today, talking about proving multi-particle unitarity with the Landau equation. So,
thank you. Yes. Hi, everyone. Thanks very much for the invitation and for coming. I will be talking about this recent paper that we wrote with Amit Sever and Miguel Correa. And if I say something wrong, it's probably because I haven't understood it, but Miguel will correct me. He's online. There is no the topic is 2-to-2 scattering of massive. I will consider scattering of relativistic particles. I will consider them to be scalars and then to be identical. So the main object, which I will be talking about, is the relativistic amplitude, which is a function of energy and the angle. And the only connection to string theory probably is that you can think of this as a scattering of pions or scattering of blue balls in large MQCD, and therefore described by strings, but I will not care about it. I'll just be interested about the properties of this object. For the technical comment is that I would consider the particle to be lightest. So you imagine a quantum field theory with some stable particle, let's say it's scalar, and it's the lightest scalar in the theory. Another little technical comment, I imagine, again, this is maybe, so the fact that the particle is lightest will be eventually important, but another comment I'll make right away is that I assume my theory has zero symmetry and the particle is pseudo-scalar. So there is no something like Q, the vertex, this is pseudo-scalar, is not allowed. So effectively, the vertex only apply to the 4 pi allowed. But in invariant terms, this is okay. So the question we will be asking about this object is, well, famously, if you want to understand this object non-perturbatively, there are some general principles which it obeys, and one of the important principles upon which we can try to bootstrap this scattering of points, so whatever is analyticity, and in particular, you can ask what is there is some analytic functions of S and T, and there is some domain of analyticity which you can say prove from axiomatic quantum field theory, but there is also a set of there is an analytic structure which imposed on this object by unitarity, and famously, so the sum of the non-analyticities of this object follow from unitarity, and this is the question that we asked about the amplitude in our paper is, okay, what is the analytic structure of this amplitude beyond slightly what was analyzed before? I will explain. So let me be very concrete. I was and start with yes. In my talk,
you talk about extending the looking at the properties of the function beyond the analytic domain that was
yes,
conjectural.
Yes, definitely. And yes, my talk will be mostly pictures. So there will be one formula, and then will be just a lot of pictures. So let's start with the first picture. So the first picture, I said 3 things, but let's be concrete. Let me draw a first picture. And well, these pictures will be graphs. And the graphs will have 4 external legs. And this corresponds to, say, incoming particles and outgoing particles. And I will think, somehow I will think about these pictures in 2 ways. So let me state it right away. And so the first way you can think about this picture, and this is more familiar to everyone, I assume, when line is a propagator, then this is a Feynman graph. Of course, this is, you can think of this as a Feynman diagram, and you can compute it and get some answer. Now, this is something very perturbative, and one important point is that I mentioned scattering of pions. I will be interested in what non-perturbative properties of this object. Therefore, Feynman graphs are not enough just by themselves. But there is another way you can think about this graph, and is the following. If you imagine that every line on this graph corresponds to the on-shell particle, and usually when we would like to put particles on shell, we can say Feynman graphs, we draw a cup. So let me draw it, but it's not necessary. If you think of this, if you think of every line being on-shell particles, then let's say there are n lines, then there is a natural interpretation to this graph that, well, you have starting two particles, you form n particles, and then n particles form two particles again. And this is example exactly what I told you, that unitarity leads to some non-analyticities of the amplitude. And this is a famous non-analyticity if you take this continuity in this variable of two amplitude, this non-perturbative formula. You have a sum, integral of phase space, and sum over number of particles from 2 to infinity. And here you have e to the n. So then, from the point of view of, and this is unitarity. So from the point of view of this formula, you can think about this graph as representing the nth term in the sum. So you take the cut, meaning you take the discontinuity of t to 2, and you write it, and you say that there is a term with n particles. Now,
and here you don't assume they are scalars, right? They can be anything.
Your
theory is general.
Can be anything, exactly, yes. Now, of course, you can also ask the same question about Feynman graph. Where does this Feynman graph and this discontinuities related to this process are called normal thresholds. Normal thresholds. They're familiar because the basic expressions of unitarity, and the break point here for the term at nth term will be n squared. This energy, this is when the energy, incoming energy, is enough to form n particles. You start having a branch cut. So now you can.
You're assuming there's just one kind of part?
Yeah. Now, what does this correspond to on this? On the Feynman graph side? Well, on the Feynman graph side, you can also take the discontinuity of the Feynman graph. Rules for doing that. Well, and the rule basically is that you take all the particles on shell, it's Katkowski rules, but you can even ask a more crude question because we do not really care. This is a Feynman graph. We do not care what is its discontinuity, but what we care from this discussion, where does it start? So this fact, for example, the fact that it starts at this point is really, it's a non-perturbative. It has nothing to do with perturbation theory. And so to go from the, you can ask about Feynman graph, where does its non-analyticity start? This question is formulated by Landau equations. So Landau equations are nothing but, it's a set of equations which tell you when a Feynman graph develops some non-analyticity, and more precisely, if you take a Feynman graph, and let me just write it. So if you have a Feynman graph, you can introduce Feynman parameters. You have integrate over loop momentum. You get some expression like this. You have maybe a delta function or some other Feynman parameter. Doesn't matter. And then you would like to, because you think of this integral as integral in some complex plane with some contour. And if you want a complex integral to develop singularity, you want a pinch. So you have, say, two poles, two zeros of D. They come and pinch the contour, and it develops some non-analyticity. And Landau equations are for each every variable alpha I, you require that you have a double zero of D. If you have a double zero, then you can show that, okay, potentially develops a pinch. Now, this is a formal way to write Landau equations, and okay, you can apply it to every graph. But there is another way, which is also you can formulate, is that the solution to Landau equations correspond to movies to some classical processes in a complexified space-time. So you take, say, Minkowski space, and you can take a complexified Minkowski space, and then you impose all particles. Well, so second, you impose that interactions are local, and energy momentum is conserved at every vertex. And finally, you assign to each particle, which is on shell, some space-time interval. You can think of alpha I being some proper time. And then the statement that you can think of this process as some process in a space-time means if you go around the loop, if it's a closed loop, then the distances should sum up to zero. So then you can think really that this is something happening in space and time. Yes, if in space and time I draw a loop, then sum over, say, differences for intervals should sum up to zero on every loop. So you can check that this is the same as this. These two equations are equivalent. And but then you see also already from this side already that it's it has a chance to be related to something non-perturbative because all the particles involved are on shell. And if all the particles involved are on shell, then we do not talk about Feynman graphs. There is a chance that this is related to some non-perturbative properties of amplitude, and here we saw it immediately exactly to be the case. You draw this graph. What is a space-time movie? Well, you take two particles with, say, total momentum 0 and total energy being n times m. These two particles, say, approach each other. They interact at the point. They form an n particles at rest, which just propagate in time, and then this n particles decay. So this is a space-time movie for the solutions to Landau equations of this graph, and it corresponds to the normal threshold. Anyhow, this is just a review, and the famous fact related to that, which is due to Coleman and Norton, that if you are in a physical region, which is, by physical region, I mean the part of the kinematic space which you access in a physical experiment. For example, for the 2 to 2 scattering amplitude, we should take S, say, larger for n square, and then C negative and larger than something. Then this is a physical region, and then Coleman-Norton proved that if you want to have a singularity in a physical region, say it's Feynman graph, then all the parameters have to be positive. And sometimes, positive and real. These are called sometimes alpha positives and alpha positive solutions to Landau equations. And well, they're important because of this. Because of these reasons, for the 2 to 2 amplitude, the only singularities in the physical regions are normal thresholds. Because this story is boring. But in our work, and I will explain why, we also will talk about alpha positive solutions to Landau equations, but you should not confuse it with this statement. So this was just a review, and here
Is it probably Feynman graphs?
this is for Feynman graphs, but we also say for the physical region, this is the only singularities that exist for non-perturbative amplitudes, right? It's just normal thresholds. If I take T negative, then we only know that the only unknowns that we have are normal thresholds coming from unitarity. Otherwise, well, we could have anomalous thresholds, but I'm considering scattering of lightest states, and therefore there are no other singularities for negatives.
On the physical domain, everything should be physical. This is what you say. All the singularities are the physical.
Yes. And but this Tolman Norton was done for Feynman graphs. There was a question.
Yeah, this picture, there is no other excitation below 2n. Isn't that like very perturbative? Like non-perturbatively, you might expect your next resonance or whatever state of particles to be in the same order.
Yes, so resonance lives on the second sheet, right? So you don't see that there. So if we plot the S plane, so resonance is so if I introduce a notion of say physical sheet, something that you can relate it without crossing any normal thresholds to the physical amplitude, then say if I use I-epsilon prescription to approach it from above, then the resonance lives on the second sheet. There are here bound states in principle. And for simplicity, we can restate everything for the bound states. And it's true that we can have bound states in the non-perturbative theory, but say for pions, there are no bound states. There is a raw resonance, but it's on the second sheet. So for pions, this is correct. So this is not a perturbative assumption. Now, this is a very simple, okay, there are normal thresholds, there are Tolman-Norton. So this story, I don't have nothing new to say, but
So the error, the logical error is that if you're in the physical region, then the alphas have to be positive.
yeah,
But the other way around, if the alphas are positive, you can
No.
have singularities also.
no, yeah. So in fact, what we will study is exactly alpha positive singularities not on a physical region. That's our work is about alpha positive solutions to Landau equation on a physical sheet, which allows T to be positive and S to be positive. And this is my next example. So far, I think it was just a review of some basic properties. So if it's not clear what we will be doing, it should not be clear yet. So. As I haven't explained. So I will explain next layer of complexity on top of that. So these singularities are very simple. There are normal thresholds. They're related to unitarity. So let me now introduce a second layer of complexity, and then the third layer of complexity will be what we have done. So let me to introduce a second layer of complexity. Let me draw a slightly more complicated graph. And I will again review this relations to unitarity on example of a slightly more complicated graph. So a slightly more complicated graph looks like this. Let's take this diagram, and again, if you're more comfortable, think of this as a Feynman graph. It's fine. So there's here's a graph. Now you see that if we think about normal thresholds, sure, this graph also has if you read it like this, so if this is a S channel, if you read it like this, it corresponds to two intermediate particle states. So if we take a discontinuity in S, we will have some unitarity which relates to discontinuity of this amplitude to 2 to 2. Now, if you read this diagram from the T channel, it corresponds to the same. Again, there will be a normal threshold, two particles going to 4. However, the new feature of this graph is that you can now take a double discontinuity. So it's clear that it has a single discontinuity in T, it has a single discontinuity in S, but the new feature is that it has a double disk. And the double disk you can check by just computing this guy. Also by theta function. So, and the support of the double disk has, say, for this diagram, it will be just here. So there is when this guy is positive, then we develop a double disk. And notice that both S and T are positive. This does not correspond to the physical region. This is not for physical scattering. You correspond to S to be, say, larger than 4 square, and T is negative. So you do not see this in the experiment, which does not involve, at least in momentum space. You can see it in impact parameter space, but you do not see it in momentum space. So this shape where the double disk is developed is called a Landau curve. And if you draw a similar diagram but in the cross channel, you will have another curve like this. So there is this picture for the support of the double disk coming from these two diagrams. And okay, you can now ask, what about the non-perturbative side? This is a graph. I told you before that we should think about these Landau curves in a non-perturbative fashion. It's not just about graphs. So can we see these curves on the just starting from unitarity? And the answer is yes.
That's a question from Volodya. I don't understand something basic. This is only one diagram, yes? But in principle, there are many diagrams. Like you can rotate this one by 90 degrees, it will be another allowed diagram.
That's right.
Somehow intervene into this inspection of singularities, yes?
Yes, exactly.
Or it will be a different singularity.
So for this, if you rotate it by 90 degrees, this is the curve that I draw. So for just this diagram, the support is about this curve. If you rotate by 90 degrees, it's like ST crossing transformation. You will get the ST cross.
But there are other diagrams. Also.
There are other diagrams, and that's exactly what I will. That's what we discuss next. Yeah, this is an example. And now, what is the relation of this example of this Feynman graph to unitarity? So the relation is this: we take the disk S of T 2 to 2, and let me restrict, for example, S to let's say 16 square and larger than 4 square. In this way, when S is between 4 and 16, I don't know if you can see people who are online here, but when S is between 4 and 16 square, there is no enough energy to produce more than 2 particles. I assume that by Z2 symmetry, there is no 3 particles, so it's 2, 4, 6. And therefore, the non-perturbative unitarity equation truncates because we do not have enough energy, and we have this equation. And this equation, so this is a relativistic phase-space integral. This equation is an exact equation. However, we usually write it in a physical region. So we write it by, say, for S larger than 4 square and T negative. However, it is known that the amplitudes are analytic in both variables. So if you can analytically continue both sides of this equation in T, and all the objects that involve admit this analytic continuation. And this analytic continuation was performed by Mandelstrom in 1958, and he got what is known as a Mandelstrom equation. And it expresses the double disk of the amplitude, 2 to 2, in terms of some analytic continuation of this guy, which becomes some sort of kernel. And instead of this 2 to 2 guys, you get a discontinuity in T. Like I denote it with this subscript. Means it's a discontinuity. Now,
Sorry, can you say what your upper index plus is? So if I missed it.
this is Hermitian conjugate.
Okay.
Yeah.
Thanks.
So now, this is a non-perturbative equation, and the difference, we don't know, of course, in a full theory what the objects are, but this theta function comes just from the properties of the Mandelstrom kernel and from the fact that these guys, they have a normal threshold in T. So just the fact that this amplitude has a normal threshold in T, say a two-particle threshold, so it's proportional to theta T double prime minus 4n squared. And this guy also has a normal threshold. And then you have a Mandelstrom kernel. You see that the double discontinuity develops as this theta function. And again, pictorially, what it means is that we should think of this graph when we talk about this yes, this Landau curve, when we are talking about double discontinuity and all the particles are on shell. It's called the leading singularity of the graph. And you see that the relation between this and say non-perturbative argument is that what we do is that in a non-perturbative theory, we will have some unknown ingredients. And these blobs signify the fact that we take some T, these amplitudes we don't know. But the point is that the position of this curve is not sensitive to what you put inside the blob. It just cares about the two-particle threshold, and therefore, to study the singularity again, we could have skipped all this argument and just started from the Feynman graph, and we would have gotten it right. And so the reason why this is the reason why people in the old days, in the 60s, study Feynman graph to learn about the analyticity of the amplitudes, because from the point of view of unitarity, Feynman graphs are the machines that solve unitarity perturbatively.
Yeah, where is the information about things like bound states or other?
Yeah, it's about it's here. When I said that this amplitude develops discontinuity at 4m squared, if you have bound states, it will be lower, and then you will predict a different Landau curve. So it's an analytic structure of these guys. So this amplitude is a non-perturbative equation, but where you develop a theta function depends on analytic properties of this guys. So if you assume a bound state,
emphasizing that the first singularity is at the two-particle threshold.
yeah, that's because I assume there are no bound states from the start. If I would assume a bound state, then you will have a singularity here. You will have
But you could have some other particle that's only produced here.
You can have, but then you will draw a different diagram like this with some new particle.
But in your argument, there's no diagram, right? This is where I'm confused about.
So in my argument, so first part of the argument is I took this, and this corresponds to the fact that there are two particles here. The second part of the argument only cares about where this guy develops a singularity and this guy develops a singularity. And on the diagram, it just means what kind of states propagate here. If you put a bound state, if you have a two-particle state, you can put any state you want. It's a on-shell state, and this will translate to the Landau curve. So the picture in my argument emerges as soon as you make a statement about where does this guy develops a discontinuity, because it develops it when you exchange some state.
So it didn't follow the calculation from down below to how you got the double discontinuity.
Yeah, I didn't explain that. So that's what. So the statement is that we can take this equation, which is unitarity, just a normal unitarity.
It depends on the kernel, right?
Yeah, the kernel is kinematical because it comes from the. It depends on the details of the kernel. You're absolutely right, but it's a known kernel which is trivial to derive. And was done a long time ago, and if you derive it, you will see that the kernel comes with a theta function such that when this guy develops a disk, together with the kernel, it maps to the theta function. But yeah, I haven't explained the details of the kernel. Miguel, I haven't explained.
Well, maybe I can ask the details later, but I think I got the gist of it.
Yeah, so the basic idea is that if I now consider this picture, if I have some theta function here, then it corresponds to some physical state, and this on the picture corresponds to the physical state that is exchanged here. And the physical state that propagates on the right corresponds to physical state here. So the idea is that no matter which physical state you choose, I can draw a diagram that will depict this process of pinching through the Mandelstrom curve.
So is it easy to see if there is a bound state, how it propagates into your lambda curve?
Yes, it's easy to see if I do it explicitly, because if you have a bound state, this guy will develop a disk at the position of a bound state, and then through this equation it will propagate to the Landau curve. So you will just immediately see by applying this equation and having a non-zero disk of t sub t, it will become Landau curve, yes. So because bound state is non-analyticity of this guy, it will just directly propagate here. So if you write here some m-bound states, so the corresponding picture will be this. So if you can alternatively, what you can do is take this diagram, and if you derive its double disk, it will be a Landau curve. And this Landau curve will coincide with what you do if you continue in unitarity and put the bound state in the disk here.
Yes, so this is a generic question. Is there an expression also for like more discontinuities, and are these useful for something? Or triple or quadruple?
On the physical sheet, at least that's that's all what we care about. That's I think you can go further if you want, because you can go for the cards and consider whatever you want. But here I'm restricting myself to just the simplest case. For this case, double disk is what we have, and the analog and CFT is quadruple disk. Any more questions about that? I can try to explain some a little bit more about it. Now, coming back to the question by Volodya is, okay, well, let's make one graph. What about all the graphs? And so again, let me assume that there are no bound states for simplicity. And in this case, all the Landau curves are known just because of this simple equation. So if you let's say you want to ask what are all the Landau curves here in this region, then you should restrict yourself modulo some subtleties to two particle graphs. So the graphs which involve propagation of two particles in the S channel, and in the T channel you can allow yourself any number of graphs. And in fact, then you see that the only type of graph you get. Similarly, you find the Landau curves, and then you can also derive them just iterating this equation. You see that if this guy, if the amplitude develops a double disk, then it will propagate into the first disk, and so there is you can now, after you found the first Landau curve, you can put Landau curve back into this equation, and effectively this corresponds to the fact that when you sum all finite graphs, they solve unitarity, and the more graphs you sum, the more unitarity, if you wish, the better unitarity works. It satisfies up to a higher order in the coupling, and at the level of this equation corresponds to the fact that if you take one graph, like if we started with this graph, we develop some Landau curve, but then you will see that okay, you start with a normal threshold here, you develop a Landau curve in the double disk, then you put this Landau curve back here. And you will start iterating and you will generate all these graphs just from unitarity.
It just means that you subtract its continuity to analytically continue further.
Yes, exactly. So you see immediately that you will have all this, Landau curves.
But why did you just describe? Can you have these many lines instead of just 2 by 2, or are you just for schematic?
Where do you want to put many lines? Here?
Well, instead of there you could have
Yeah, here you can have many lines. Yeah, sorry, that's you can have as many lines as you want, and 1 and 2 and 3, and all this Landau curves are unknown. So you don't have to compute them. There are many ways to compute them. Well, either you can do the Landau equation for this graph, or you can solve it using this kernel. In any case, I would say that here all the Landau curves are known in this strip.
Sorry, I didn't understand the argument that you solve unitarity better and better. Is it a problem that the perturbative expansion is asymptotic?
It is a problem. That's why I understood when I said that it was confusing.
So is it somehow solved when you look at the Landau curves? Like is that's
so
you get an asymptote or?
So sorry, what I mean by you solve it better and better is that if I just take one graph, if I just take this one equation and I take this disk, then it is solved up to order, say lambda to the 4. So lambda to the 4. If I want to solve it up to lambda to the 6, then I add another graph. Of course, you're right. This is a asymptotic expansion. It does not converge, etc. However, the structure of the curves is follows just from this non-perturbative equation, which does not care about perturbation theory. So when I talk about Landau curves and about solving them, and so if you want to solve it non-perturbatively, you need to solve, say, this equation. And final graphs, they solve it perturbatively, but non-perturbatively, one has to complete it. And there is an interesting story about how people did it in the past. It's a whole separate story. Essentially, you can try to use this as think of this as some map in a functional space, and then in some situation this map is contracting, and then you have a fixed point, and then there is this kind of non-perturbative way to solve it. But yes, non-perturbative unitarity is expressed by this, and all I'm saying about that, whatever solution there is, it will exhibit all these Landau curves, which can also be depicted by these graphs.
Sorry, do you assume at some point that there is no other stable particle? Because it seems that you need to have some.
Let me just emphasize again that here I'm working with the setup where I have just a single lightest particle, just one particle which is stable, everything else decays, there are no bound states.
All the other are unstable.
All the other unstable, there is just say pion, no bound states, everything else decays. If we have other stable particles, we can generalize the story. It's just you have to put all these other thresholds and etc. But the story is the same. It's just now we have 2 types of propagators. It will be more complicated. The idea is the same. So and the way not something crucial here is that to run the story, I assume that the energy is low enough, and this allowed me to avoid talking about multi-particle amplitudes. And because in the unitarity equation, all translated at 2 to 2. And that's why it's simple. That's why, say, these regions are easy to understand, and then in some sense solvable for the Landau curves. So what we did in our paper, we looked at the next more complicated region, which is this. So let's say we take 16 here, 16 here. Let's take 36. So let's look at this in this region. And now we see that if you try to play the same game, let's say we start with S between 16 and 36. The unitarity equation will involve a new term. So we have now this S equal to 2 is equal to, first we have plus PS4. Now, in principle, one can go and play the same game and try to derive this Mandelstrom kernel for this term. And there are a few papers about that. However, because it involves multi-particle amplitudes, it's much harder. So this hasn't been really much explored. And instead, what we will do is that we will ask a simple question about Landau curves. And for this, then, instead of, as I hoped that I'm motivated by now enough that, okay, we can go through this path, and this is a non-perturbative path, but equivalently, at least for this kind of minimal set of singularities, we can just analyze the Feynman graphs. So the idea is, therefore, we will not try to analytically continue this. It's an interesting problem. It would be good to solve it, but we will now try to understand what is a complete set of graphs which gives Landau curves here.
So are you conjecturing here that this feature will work and
yes.
Try to apply it? And
yes,
check
yes,
it?
yes. Well, I think it's doomed to work. I don't see how it will not work because it kind of works by construction. If you start with
it certainly works for perturbative theory because this is what it is. But
yes, but here, so it's just when we look at the Feynman graph, it realizes the structure manifestly. You know, it satisfies this equation with the leading order. And this guy T2 to the 4 in the Feynman graph, it will have the structure of a normal threshold and the dual channel. It's just, it will have this simple structure, but the cut is there still. So I guess we can discuss the failure modes, but let me just now assume that going from this complicated vertices here, which comes in the non-perturbative theory, to shrinking them to a point, and thinking about this as a Feynman graph, I'm not losing anything. So, okay, let me try to explain again. The idea is that yes, there is a task of doing this analytic continuation, and we can encounter some exotic singularities maybe on the way, which has a non-perturbative nature. However, whatever we are, we expect to recover just the normal thresholds. You know, this guy will have normal thresholds and other channels, just because it's some basic things which follow from unitarity. And the Landau curves that we will get by analyzing these graphs are exactly of this type. So they will be there in a non-perturbative theory just based on a very, very weak assumptions. Now, it could be that in the non-perturbative theory there is something exotic, crazy beyond that. However, we do not have a good reason for that. So, in a sense, what we are doing here, we are studying unitarity, right? We are studying a robust features of unitarity. If you assume this equation, it imposes new singularity on you by analytic continuations. And so we just say we start with normal thresholds. Here you see we start with the normal thresholds, and we discover the Landau curve. So we will now just continue this further. That's the idea.
I guess you could maybe say that there's a story to be told where you start from unitarity and derive the Landau equations. Then you would never in your talk have to say Feynman graphs again.
Yes,
that should not be too hard, I think.
Yes, I think that's true. So this Landau equations, they follow. In principle, I could never talk about Feynman graphs and just talk about these kernels and pinching and assuming what I'm doing. However, what we do in practice, and for the rest of the talk, I will be dealing with graphs, with Feynman graphs. But I just want to emphasize that the picture that we have in mind is this. So it's a non-perturbative picture because we're only talking about a set of singularities, and set of singularities that do not care about the detail of the graph. You can put any vertices here, any derivatives. You can put some form factor. It will not change the fact that you have this theta function. So that's a basic idea why these computations are robust and why we can talk about Feynman graphs. It's clear. So yes, so the basic idea is now, well, you see that here the picture was we had two particles in one channel. Now if we go here, the intuitive picture is that we should be talking about graphs of this type. This is just an example. So why is it a reasonable graph? Because you see it starts with a 4-particle cut in the S channel. It starts with a 4-particle cut in the T channel. So you expect it to be here between 16 and 36 in both channels. And indeed, this Landau curve, see it's there. And this is an example of the graph which solves my problem. Now,
if I may ask, I mean, here you write an example of a Feynman diagram that has a right cut, but you can write any other. If I understand from your discussion, you don't care which one it is. It's just that.
No, you don't care what steps in the vertex. What you see?
But you have a contribution. It will depend on how you have the same number of particles in.
Yeah. So what it depends here on, it's on the structure of the on-shell states. So if I have this graph, then whatever I put, say here, I will recover an example of a singularity. This corresponds to the fact that I take the unitarity cut, first cut which has 4 particles, so 4 particles on shell, and then I continue this guy, and I study that singularity comes from normal thresholds in this channel. So again, there will be some normal threshold in this amplitude, there will be pinch with the Mandelstrom kernel, and you will find some theta function which is a Landau curve. However, it is not sensitive to what I put, the details what I put here. It's only sensitive for the structure of the on-shell states and the contraction of the phase integral with this analytic structure. That's the basic idea. But this is not the only graph we can draw with this property. So that's exactly.
That was my question. That if you can write the same type of graph, which will have exactly the same tree-level in spirit type thing that will contribute.
Yeah. So,
but with a different draw.
Yes, the idea is next that, and that's exactly what we want to do now is to classify all the graphs which have this property that you can interpret them as analytic continuation of this 2 to 4 guide and probing some singularity in this process, which also follows from unitarity, and you can also interpret it as analytic continuation of 4-particle unitarity in the other channel.
So all the graphs that have the same maximal cut.
They will have they will not have the same maximal cut. They will have the same normal thresholds, but the maximal cut will be different. It's a little bit like you can have. Well, let me draw another example because it will maybe become clearer. So at this point, I would like to tell you now what's the problem that we are solving. And the problem is the following. We would like to find all the graphs which satisfy the properties that first they come from the analytic continuation of this 4-particle unitarity, and in the graph theoretical terms it corresponds to the fact that every leg you can cut either by 2 or 4-particle cut. So let's say in the S channel, this is a 4-particle cut. You pick this leg that corresponds to a cut in the T channel, which also is a 4-particle. So we're looking for the graphs which are, say, 4-particle on both channels for every leg. And then the non-trivial part is that we just don't want to find all these graphs, but we also to find that they have the solutions of Landau equations. So we want to find these graphs first, and then we want to solve Landau equations on these graphs and check that there is some solution. And moreover, we want to impose that this solution is alpha positive. Again, all the alpha i's in this Landau equations that I draw are positive, and this is related to the fact that I'm interested in singularities on the physical sheet. I said the word related because there is some story to be told here, but let me just now practically say what we've done, and then we will have a discussion. So the task at this point is, in principle, the one you can give it to high schooler. For starters, just start drawing pictures which have these properties. You draw a picture, you try to find all these pictures which have this property. You cut it, you have 2 particles, and you cut all the legs. All the cuts are 4-particle cuts or 2-particle cuts. And in fact, at first we spent half a year maybe trying to play this game by hand, and then we thought, oh well. And the intuition is simple. You think, okay, well, let's say I try to add some vertex, you randomly add some vertex. you see that if you end up randomly add a vertex, you violate my rule. Now you have a 6-particle cut here. And so we said, oh, okay, it's clear that because we want to have 4-particle cuts, we are not allowed to add vertices. And so we should be able to solve this problem easily. But then 1 month has passed and we found another graph and another month, and then we found another one. So it became clear that we don't know what we are doing. And we should resort to some power of computer. And
Just you wanted to give this to a high schooler?
So yes, so we eventually, after half a year, we realized, okay, this is hopeless. We should just do brute force search. So we just start drawing all the graphs, and the task with this is, of course, there are infinitely many of them, and we try to select those which have these 4-particle cuts. And of course, this problem is not solvable by brute force because the way we do it is that we fix a number of vertices. And then we run our codes. And when I say we, it's Miguel who ran the code, and then we get some number of graphs. But then, okay, you go from V to V plus 1, and you know the number of graphs grow factorially. So you very quickly, you seem like you're doomed, that you will not be able to solve this problem because, however, what happens, and this is related to the simple intuitions that I told you, if you add a random vertex, you introduce more than 4 particles. We found that, in fact, for this 4 particles guys, the number of graphs drop significantly, and we can quickly identify all the graphs, and then we can extrapolate, and this is of course a conjecture, to V going to infinity. And so we believe that we identified all the graphs. I will tell you now more. Yes, and this problem was first, in fact, there was a paper in '61 which was solving exactly this problem. It was called the nearest singularities in the pi and pi scattering. They were just doing exactly this, but I wouldn't be standing here if we found that they got the answer wrong by infinity. So we found this infinity, and that's what I would like to tell you. Because it's,
You mean they found a finite number, or
they found like 3 graphs and they're infinitely many. So, so that's let me now. That's what the main result, which is just a set of graphs. So now it's the drawing part.
So the first graph, you are infinitely smarter, or you just have a better computer?
Better computers. In fact, we are lucky that there was some nice graph theoretical software which mathematicians developed, and I think the one we used is like 1 year old or something. So no, I think they were smarter because the way the tricks, they did some crazy tricks, but we were doing just simple things. So, so the first graph I already told you, and this will be a special graph. So that's the first graph. Now another one. And you can check that all the cuts are 4-particle cuts. Well, it should be 4 or 2.
Can you show the 3 that they found by hand?
I don't remember which ones. Well, I know the simple ones. I will show you the few of those they found. But and by the way, it's important that I'm drawing the graphs that have solutions, alpha positive solutions to Landau equations, because you might say, oh, but you know, what if you remove these 2 legs, for example? What's wrong with that? Or so sometimes what will be wrong with that is that you do not have a solution. And so I'm almost done. So there is this graph. And okay, so these are special graphs, and there are two infinite families, and these are the two infinities that they missed.
It's already more than three, but
Yeah, so they missed a few more. So they missed infinity plus one, something like infinity plus two. So okay, so now there are the interesting guys. The first, again, this also after you see them, it becomes trivial. But first, we didn't figure out that they exist.
It's clear. I understand why the cats is in the S channel.
Yeah.
Does it have to be vertical in these pictures? Can I?
It will be what?
For example, the first diagram you drew.
Yeah.
If I cut like the diagonal.
Yes, you can cut a diagonal, but the point is that there exists a four-particle cut. It doesn't have to be. It doesn't say that every cut has to be so, but there is a cut. That's important. Yeah. And so now, yes, these are the interesting ones. This is the infinite family. Dot, 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 dot. So you see the basic idea. You can have triangle chain. So you have a three-particle cut everywhere here, four-particle cut here. And that's the first graph, and the second graph is the same, but you just make this link here non-planar. So you just have the same graph with okay. So these are all the graphs. Again, there is an infinite many of them, and just to give you some idea, let me show you how we did it in practice. For example, you start with v equals 12. That's the highest v we took. So you first you generate all number. The complete number of graphs without, say, something we call bubble chains. It's some trivial ways to reduce the graph, doesn't matter. So, but the complete number of graphs here is 3, 5, 8, 7, 7, 9, 3. So it's a lot of graphs. And then you start imposing constraints and say, first we impose what we call non-trivial triangles. Effectively, there is some things that if you want to solve Landau equations, it means that locally you should also solve Landau equations. And sometimes you find the subgraphs which do not admit solutions to Landau equations, and you can drop them. And so our first step is non-trivial triangles. And
Yes, I'm sorry. And suppose you have some mixture of these two graphs, like half of this line with triangles goes up and half of them goes down. What will be wrong?
So as the claim is that well, nothing is wrong, but you should make sure that there are just four-particle cut. So every leg can be done by the four-particle cut, and then we should also allow for automorphisms. And the claim is that whatever the other cut you will try graph to draw, it will violate this rule. So in other words, we will get some cuts which are more than four particles.
And the positive alpha condition.
Sorry, and also we impose that alpha is positive, and this is related to the fact that we are looking for singularities on the physical sheet. But in fact, for the lightest particles, again, this is maybe something to discuss. We hope that this is a complete solutions. Of course, this is a great problem to show that, yeah, so the answer would be either there is no alpha positive solutions. So for example, you will develop some kind of triangle which does not admit the solution to Landau equations, or it will have more than four particle cuts. So these are the basic two things we impose.
So you're saying that there, if I cut through the triangles, then I will not see the four-particle cut in the S.
No. I'm saying that you will see the four-particle cut. So
But I see more particles in the T channel.
no, in the T channel you can cut them like this.
Yeah, but what if I don't?
There just has to exist.
They have to exist. They have to exist. Yeah. So you will find the cut, but it will lie higher in the Mandelstrom Equation. Now, okay, so this is let's say we found that. Please.
It just has to exist a cut.
Through every leg, every leg should admit a cut, which is a 4-particle cut. Every leg. So you say, let's say you pick this leg. So there is a 4-particle cut. You pick this leg, there is a 4-particle cut. So there is this leg, there is a 4-particle cut. Leg is 4-particle cut. You should be able to cut every leg with 4-particle cuts.
Why every leg?
Because we are looking at what's called leading Landau singularity. If you don't cut it, it's equivalent to the fact that you start contracting the graph, and then it's just redundant. In principle, you can ask, okay, why didn't you consider, say, higher degree vertices? All these graphs are 5 to the 4. Well, in fact, here this guy is 5 to the 6, and the claim is just if you try to draw any graph, if you try to impose this condition. These are all the graphs.
So if in this one you remove all the triangles, you don't find the graph in any of the other.
If I remove,
you can add as many triangles as you want.
Yes.
So you can also remove them, and it's different topology than any of the 5 or 6.
Yeah. So the first graph, and these are someone asked what are the graphs that they found in the past. So if you take the first graph on this chain, this is plane across, and this one, of course, they found, and in this one, it's a non-plane across, and this also, of course, they found. So yeah, these are two graphs which I didn't draw here because they belong to the families. So now what we did is and here let me tell you, okay, you have non-trivial triangles, and you have a reduction, and then we impose that there is at least 2 or 4 particle cuts exist, and then produce it further, but then 2 or 4 particle cuts exist. But then when we say that all the legs should admit 2 or 4 particle cuts, this is this is a computational expensive step. We go to 9, and then if we impose also, there is a notion of a trivial box. Trivial box, it's a subgraph which does not admit a solution to Landau equations. Then we reduce to 3, and then we reduce to 1 by solving Landau equations, say numerically. And the 2 graphs which do not admit a solution, you can take this graph and instead draw something like this. Or you can do the same thing on the other side. But the claim is that if you try to solve Landau equations, you will not find the solution. So you see from this game that, if I would be telling you this, just that's what we found, this is hopeless, because what if there is some other thing? But so why we expect that we did it right, because we just did a brute force search, and then at the end we reduced to one graph, and this one graph, it's just because there's 2 chains that I drew before. They sort of, one has even number of vertices, and say this one has 4 and this has 5, and if you add triangles, it will have 5, 7, 9, 10, 11. This has 4, 6, 8, and so at v equals 12, you'll just find one graph. And so we get the same thing for v11. It's one graph. What v equals 10, one graph. And so we believe that by extrapolation, that okay, these are the only things that are there. Of course, it's not a theorem, but that's what we did.
How do you know nothing will go wrong if you take too many of them?
Nothing. V to be large.
You said you have infinite family. What if some other crazy thing happens?
Oh, then we are wrong. If some other crazy thing happens, then we just, what I say is incorrect. So we just believe that because of the basic intuition that adding vertices while preserving 4 particles is hard, you tend to increase. And then we just did an explicit search, and as far as we pushed, no crazy things happen. So here it's just a pure assumption that it doesn't happen.
So, sorry.
Yeah.
Your sort of special graphs here on the right, they end at, what is it, 8 vertices, right? Those guys. The maximum number of vertices.
The number is 6, in fact. Here there is all these guys are 4. Because this is non-planar, so this is 4, 4. The only graph with 6 vertices that we found is this, and this. The total number of the total number of vertices here for the special guys. It's well, it can be, you count 1, 2, 3.
I thought 8. Yeah.
It's 8. Yeah. This is 8.
So V equals 8 is where special things happen.
Yes.
And then so at 9, 10, 11, 12, you see 1.
Yes. Exactly. Yeah. So at low number of vertices, special things happen, and then after V equal, starting from V equal 9, we just see 1, 1, 1.
Okay.
That's what we observed.
So 4 ones is what you extrapolate.
4 ones. We extrapolated 4 ones.
Okay.
To infinity, yes. So let me now draw the curves. Yeah.
We over 1 hour, so maybe.
I will just I will just draw the final plot, and I will.
So the criteria to isolate this graph, you had to use this alpha positive.
Yeah. Because yes, we are imposing to alpha positive.
What does it mean on the physical sheet? Because you're cutting through 2.
Yes, so it means that, so if you have, say, let's say you start with S and T, and you have this, either if you like this graph, and this unitarity cuts, and then, well, let me go to the Mandelstrom triangle. I start here, amplitude is analytic here, and then I continue without crossing a normal factor distribution. Or I can go here. So now the punchline of all this is that I should find all these graphs. Okay, that's what we did. And now I should find all the Landau curves for them and plot them. So that's what we did.
Why can they put triangles in those ones?
Sorry?
Why can they put also triangles in this one?
Yeah, so you can start doing things, and the claim is that you will find that they will not have alpha positive solution for Landau equations. Yeah. So yes, this was of course simplifications. We chose the rules of the games are such that all these factorial growths of graphs seem to.
What is the argument for demanding this alpha positive?
Yes, let's discuss this later. Yes, because in fact there is no argument. But
okay.
But no, there is some idea, but no argument. So okay, let me now draw the things. So let's start from 16 to 36. And well, all the curves look effectively very similar. They're just some kind of curves like that. So I will not draw the detailed structure. You can just plot them. They'll look like this. They have some layer. And there is one important property which is the following. There is a special curve which corresponds to this graph. To which the triangle chains accumulate. So, let's say you take a planar triangle chain, and let me use so this red color for that. So this is the first planar cross. Then you add to it one triangle. So anyhow, this one is skipped, but you start adding, and what you find that all these Landau curves very quickly accumulate to this curve from above. And in physical intuition is somehow that when there are many of these triangles on the solution to Landau equations, you can collapse this triangle to the three parallel particles, and then you get this graph. But okay, this is just words. We found the numerical solution to Landau equations, and they accumulate. Now, if you take the non-planar cross, it starts somewhere here. Then the non-planar guys also accumulate. So the basic result is then, okay, we have this, we believe that we have all the Landau curves, and there is this new phenomenon which does not happen for 2-to-2 particle, and it is related to multi-particle unitarity, that Landau curves accumulate. So there are infinite, you could have thought, and that's how when we started this project, we thought, okay, well, we'll find a few graphs, but in fact, there is an infinity of graphs. And after you see this infinity of graphs, then it's clear that in this multi-particle region, so as we go here, these infinities will be completely ubiquitous, because you start with any graph like this. For example, and then you imagine that you can take this set of lines and you turn it into a braiding chain of particles, which will do something like this, and then we will find an accumulation curve. And so it seems like accumulation curve will generate another accumulations of accumulations, and there is a very complicated structure of analytic of these Landau curves for the amplitude. So this should be true for scattering of pions. And then there will be many of those, and in this sense, these accumulations will be completely generic, and there are many of them. Just somehow we found the simplest one and studied that. And yeah, so this picture is our basic result. And let me just finish with some few general comments. So there are a lot of questions you can ask. Say, first. Like Benjamin usually asks me at the end of the talk, so what? The practical application, what do we do with that now? So, okay, that's a good question. One application that we can think of is that when we do the S-matrix bootstrap, usually imposing multi-particle unitarity is very hard, and we never do that. And so here the idea was we are studying the shadow, sort of the shadow that multi-particle unitarity casts on the 2-to-2 particle amplitude. And we see that the shadow is such that below this leading curve, now that we understood all the curves and we believe this is correct, below this leading curve, you can impose the Mandelstrom equation. So the idea is that in principle, when we do the S-matrix bootstrap for 2-to-2, then there is an extra equation to be imposed in this region. And the fact that it's this region is a manifestation of multi-particle unitarity. So this is something very practical. But more generally, I guess this structure, it should emerge. It's some reflection of multi-particle unitarity. And if we want to understand for the S-matrix bootstrap this multi-particle amplitudes, we should be able to understand what exactly is the mechanism from the point of view of unitarity kernels of emergence of these accumulation points, and whatever multi-particle model, if we want to build, it should reproduce this. So it's some generic feature of relativistic amplitudes. Yes, and there are many questions. Like Miguel was asking, why did you focus on alpha positive solutions? And so the reason is that the idea is that when we start on the physical, sheet, it responds to undeformed contour. So alpha goes between 0 and 1. And if you believe that if you want to study pinches like that, then this is alpha positive, because alpha is between 0 and 1. However, when you go to this unphysical domains, you can imagine a situation where we start with a contour, and as we analytically continue, so Coleman Norton tells us that the physical singularities are all this type. But let's say we have some pole, and it drags the contour, and then suddenly there is a pinch somewhere here. And in fact, so when in the 60s people tried to solve the prove Mandelstrom representation, that was exactly the problem, because there is this famous singularity called an Eck node. And X naught is precisely this. When you start with a physical region and your contour get dragged, and then you have a pinch of complex alpha. And there is no system understanding of the emergence of these singularities, but there is this conjecture. I guess you are one of those people who likes to use it, which is if we consider lightest particle scattering, then we have maximal analyticity, and this thing does not happen. And so I like this conjecture, and I think it would be great to understand why this does not happen. And in all the studies, people found that when we consider lightest particle scattering, this kind of stuff, for some reason, does not happen. But there is no understanding what is the mechanism for that. And one of the, I would say, the biggest, and this is related. So this is non-alpha positive. And so when I draw this picture and I say that that's what we believe is correct, I assume that for lightest particles, this does not happen. And this would be this is very interesting to show and to understand what is the mechanism that screens all this crazy stuff from happening. That's a basic point. And of course, also coming from the story to ADS, all the structure should come from the structure. So we are used to study double twist operators. They're simple, but if you go to multi-twist, we should start seeing this crazy stuff also. Multi-twist analysis much more complicated, because multi-twist is the same as multi-particle. So all this complicated structure should be also there emerging. So yes, thank you.
Okay, so any questions? Comments?
Maybe one question. Since you rely on the Feynman diagram, if I don't assume that what I allow myself to call a conjecture is true, this would still apply for any perturbative theory, right? This would be a proof for any perturbative theory that at least you have this kind of singularity.
Yes. Yeah. So I have in mind non-perturbative, but yeah, for perturbative, that's what we were doing. Yeah. So in perturbation theory, in fact, all these conjectures. The idea is that if you want to prove something like this, I do not, but at least I do not believe that we will make progress ever in non-perturbative in this. But in the last 60 years, there was no progress. But we can make progress in this understanding the structure of graphs. And so then the idea would be that we prove something for the graphs, the perturbative graphs. So you prove that they do not admit certain singularities, and then you assume that this happens in perturbative. This is an assumption.
Okay. Any further questions for people online? Well, we already have several questions in the
So I can ask maybe one last one.
Sure.
Do you see hints of this structure in the structure of this four-particle phase space kernel? Did you look at it to see if it's inconsistent with this or not?
Well, it must be. Yeah. We haven't checked, but because well, no one has done the exercise.
Well, it must be. I'm not sure because you made several assumptions.
I think it must be, because there is really no assumption. Let's say we do the first cut. You plug in the four-particle kernel, just this graph, and it will have this singularity, and this singularity comes from iteration of unitarity. It will have to be there. But it will come from this. It should be maybe coming from the structure of the 2 to 4 amplitude close to this four-particle threshold, maybe with some other continuations. So we haven't done that, but I don't see the way how you would avoid that. It's just, it's the set of things that come into getting this curve is absolutely minimal. It's a phase space, and the fact that the other guy has a singularity is dictated by a previous iteration of unitarities. Of course, no, you can say, well, there is some crazy non-perturbative cancellation. I don't see why. So it should come out, yeah. But we haven't done that. There were a few papers in the 60s where people understand this analytic continuation for the 3-particle kernels. But already those, for those who work on this matrix bootstrap, they have 1 or 0 citations. So it's kind of a dead end. It should be possible to do it.
Okay. If there are no further questions, let's take question 1.
some organizational. So we have a couple of rooms booked for people who need a room in Paris working. So apparently there was some misunderstanding. So both of them will be available from like half an hour from now. You can just ask